June 14, 1944. 9:23 a.m., British tank commander Captain Michael Harrison peered through his periscope at the silhouette of a lone German gun 2,800 meters away, the 8.8 centimeter flak, the 88. His Churchill tank boasted 150 millimeters of frontal armor, theoretically impervious at that distance. Theoretically, the first German shell pierced his armor like paper. A muzzle velocity of 1,000 meters per second, 220 millimeters of penetration at 2,000 meters. Harrison didn't survive. His tank was one of 347 Allied tanks destroyed in Normandy that day by the 88. The Soviets were watching closely, very closely. The 8.8 centimeter Flugabwehrkanone, 18, 36, and 37, popularly known as the 88 or Flak 88, was originally designed as an anti-aircraft weapon. Developed by Krupp in Essen between 1928 and 1933, its purpose was to shoot down high-altitude bombers. But German engineers had created something that could do so much more. The weapon had an 88 mid-millimeter caliber, a barrel length of 56 calibers or 4.928 meters. The projectile weighed 9.5 kilograms and left the barrel at exactly 1,000 meters per second. For comparison, the American 76mm anti-tank gun M1 only reached 792 ms. The Soviet 85mm D5T managed 792 ms. The 88 was 200 ms faster. That meant not only higher penetration power, it meant a flatter trajectory, more precise aiming, shorter flight time to the target, and less time for enemy tanks to evade. The design was quintessential German engineering. The barrel material consisted of high-alloy chromium molybdenum steel with a tensile strength of 1,250 newtons per square millimeter. The wall thickness varied from 15 millimeters at the breech to 8 mm at the muzzle. Optimized for maximum strength with minimum weight, the projectile itself was a masterpiece of ballistics. Panzergranate 39 with a ballistic cap. The cap stabilized the projectile in flight and shattered upon impact, allowing the hardened steel core to strike the armor with maximum energy. The core hardness was 64-68 HRC on the Rockwell scale. Modern analysis shows this hardness combined with toughness was unrivaled worldwide in 1944. On May 25, 1941, the world witnessed the first massive demonstration of the 88 as a tank-destroying weapon, the Battle of Sollum, North Africa. General Erwin Rommel had positioned 88 flak guns in camouflaged positions. The British 7th Armoured Division attacked with 238 Matilda II tanks. At the time, the most heavily armoured tanks in the world. 70 millimeters of frontal armour, impervious to all German tank guns of the time, but not to the 88. In 4 hours, 123 British tanks were destroyed. The surviving British tank crews reported invisible guns that hit with deadly accuracy from 3,000 meters. British Brigadier General William Gott wrote in his report, "These German 88mm guns are a weapon against which we have no answer. The precision is devilish. The range overwhelms our tactics." The hydraulic aiming system of the 88 was revolutionary. Developed by Krupp engineer Dr. Heinrich Erhardt, it used 2 independent hydraulic systems, one for horizontal alignment, one for vertical elevation. The gunner could control both planes simultaneously with a single handwheel. The precision of the system, 0.1 degrees. That meant a theoretical deviation of only 3.5 meters at 2,000 meters. In practice, with well-trained crews, the hits were within a circle of 80 centimeters in diameter. Allied weapons of this time had scatter circles of 2 to 3 meters. The superiority was mathematically provable. The firing rate was impressive. A well-oiled 88 crew could fire 15 to 20 rounds per minute. Each projectile cost about 45 German marks in production, roughly 180 euros in today's purchasing power. An average Sherman tank cost $44,000, about $700,000 today. With an average of 2.3 shots per tank hit, that meant for about €400 of ammunition, an 88 could destroy a $700,000 target. The cost-benefit analysis was devastating for the Allies. Stalin personally ordered on March 12, 1943, to analyze all captured 88 flak guns. The NKVD report, number 472143, meticulously documents every aspect of the weapon. Soviet engineers completely disassembled 17 captured guns. They measured every part with precision tools. They analyzed the metallurgy. They tested the hydraulics. The report is 847 pages long and contains 1,243 technical drawings. The conclusion on page 843. The German 8.8 scimitar flak surpasses all Soviet guns in range, precision, and penetration power. Immediate development of an equivalent system is classified as a strategic priority. The Soviet answer came in 1944, the 85mm D-44 field gun. But it was not a true equivalent. The muzzle velocity was only 793 ms, 207 ms slower than the 88. The penetration power was 100 mm instead of 220 mm. The hydraulic aiming system worked, but the precision only reached 0.3 degrees, 3 times less accurate than the German original. Soviet veterans later called it the half-88. It copied the form, but not the soul. The production of the 88 was itself an engineering masterpiece. The Krupp plant in Essen produced a total of 21,310 guns between 1933 and 1945. Each weapon underwent 147 separate quality controls. The barrel was X-rayed after each manufacturing step. Every hydraulic valve was tested under 300 bar pressure. The rejection rate was below 0.3%, even in 1944, under constant bombing raids. American inspectors found quality control protocols after the war that showed German quality standards remained absolute until the last day of production. Captain James O'Donnell from the U.S. Technical Intelligence Team wrote in 1945, "The Germans lost the war despite their engineering, not because of it." The site of the 88 was a Zeiss Zielfernrohr Flak ZF-20, 8 lenses made of specially hardened glass, coating against reflections, magnification 4x with an 8-degree field of view. More important was the quality. The glass had an optical precision of lambda 10, deviations smaller than 55 nanometers. For comparison, a human hair is 100,000 nanometers thick. This precision enabled crystal-clear vision even at 3,500 meters. Allied optics of this time reached lambda 4 at best. The difference was decisive in battle. A German gunner could identify and hit targets that were still blurred for Allied gunners. The slide rules and ballistics tables of the 88 crews were works of art, of applied mathematics. Each 88 came with a manual, a 340-page script of ballistic data, temperature, air pressure, humidity, propellant temperature, barrel wear. Everything had its own tables and correction factors. A skilled crew could calculate the correct elevation for a moving target at 2,400 meters in just 8 seconds. Soviet analysts tried to copy these tables, but they soon discovered that the calculations were based on empirical data from tens of thousands of test firings. The Soviets had neither the time nor the resources to replicate that database. They copied the numbers without understanding the science behind them. Operation Bagration, summer of '44. Soviet forces overran parts of Belarus and found an abandoned German testing ground for anti-aircraft guns. There, they uncovered 23 tons of documentation, development reports, metallurgical analyses, hydraulic schematics, production manuals, training documents. General Nikolai Voronov, head of Soviet artillery, personally flew to the site. He spent 3 days studying the documents. His later report to Stalin, "The German artillery engineers are at least 10 years ahead of us. We can copy the hardware, but replicating the knowledge behind it will take decades." The 88's variety of ammunition demonstrated German versatility: armor-piercing round 39 for taking out tanks, high-explosive round 41 for soft targets, smoke rounds for tactical concealment, illumination rounds for night engagements. Each type of ammunition was optimized for maximum effectiveness. The armor-piercing round 39 had a 95% hit probability at 2,000 meters against stationary tank targets, under test conditions. Under combat conditions, it dropped to 60–70%, still 3 times better than comparable Allied weapons. The Soviets copied the ammunition types, but their production tolerances were inferior. Soviet 85mm shells had a dispersion of ±3 millimeters in diameter. German 88 shells, ±0.5 millimeter. Those extra 2.5 millimeters meant poorer sealing, energy loss, and reduced accuracy. The transportability was ingenious. The 88 weighed 7,407 kilograms, ready for action. The towing vehicle was typically an CDKF's 7 half-track with 140 horsepower. From travel position to firing position, 2.5 minutes with a well-trained crew. That was critical. An 88 could set up, destroy 15 to 20 tanks, and get away before Allied artillery could identify and shell the position. This hit-and-run tactic made the 88 even more dangerous. Soviet guns needed 8 to 12 minutes to set up. That was the difference between survival and annihilation. After the war, Operation Ossowa-Viakim, October 1946. The Soviets systematically deported over 2,200 German weapons engineers to the USSR, including 47 Krupp engineers who had worked on the 88's development. They were taken to secret design bureaus in Tula and Zlatoust. There, the Soviets forced them to develop new anti-aircraft guns. The result was the KS-1 Comet, an anti-aircraft missile that clearly used German technology, but for ground-based artillery, the 88 remained unmatched. The Soviet S-60 of 1950 reached a muzzle velocity of 1,000 meters per second. Finally, equivalent to the 88, but 17 years later, the psychological impact of the 88 was immense. Allied tank crews developed a specific fear of the weapon's characteristic muzzle flash and bang. American Sherman tank driver Frank Miller described it in his memoirs in 1967. When you saw the orange flash of an 88, you maybe had 2 seconds. At 1,000 meters per second, the shell took 2.5 seconds to travel 2,500 meters. 2 seconds to think, am I the target? Is it going to hit me? Is this my last moment? Then the impact. If you hear it, it missed. If not, you hear nothing anymore. Psychologists today call this the 88 syndrome, a specific form of combat stress. The Krupp engineering department, led by Dr. Erich Müller, conducted over 8,700 test firings between 1936 and 1941 to achieve the 88's ballistic perfection. Every shot was documented: propellant temperature, air pressure, wind speed, barrel wear. The data filled 127 binders. This empirical method, systematic testing and documentation, was revolutionary. Allied weapons development relied more on theory. The German methodology was test, measure, adjust, retest. The result was a weapon that dominated in the real world, not just on paper. The post-war influence of the 88's technology is directly traceable. The American M51 Skysweeper 75mm anti-aircraft gun of 1953 used a hydraulic system strikingly similar to the German one. Coincidence? Hardly. 17 former Krupp engineers worked for the U.S. Army Ordnance Department under Operation Paperclip, starting in 1946. The Soviet KS-12 85mm anti-aircraft gun of 1950 had a barrel construction that exactly copied the German design. The French AMX-13 tank used a 90mm gun with ballistic principles derived from the 88. The Swiss Oerlikon GDF-001 35mm anti-aircraft gun, developed in 1962, had an aiming system that clearly mimicked the Krupp hydraulic system. The 88 wasn't simply copied, it became the DNA of modern anti-aircraft artillery. Modern analysis of the 88 by military historians and engineers is unequivocal. Dr. Robert Forsyth, American military historian and former officer, wrote in 2015, "The 88 was a system weapon that fundamentally changed Allied tank and air tactics. Its technical superiority forced the Allies to make tactical adjustments that prolonged the war. Without the 88, the air war over Germany would have been different. Without the 88, Allied tank breakthroughs in France would have been faster. A single weapon changed strategic realities." That is rarer than people think. Training for an 88 crew took 16 weeks. Comparable Allied programs lasted 8 to 10 weeks. The German gunners didn't just learn how to shoot, they learned physics, meteorology, mechanics, hydraulics. Each crew member could take over any position. That was crucial in combat. If the gunner fell, another immediately took over. The Soviets tried to copy this training system after the war. But German thoroughness couldn't simply be transferred. Soviet training focused on speed, German training focused on perfection. The result showed on the battlefield. The 88 also had a psychological side effect. It forced the Allies to develop heavier tanks. The British Churchill tank, the American M26 Pershing, the Soviet IS-2, all were direct responses to the 88 threat. These tanks were heavier, slower, more expensive. They consumed more fuel. They were more difficult to transport. The 88 dictated Allied tank design, a defensive weapon-shaped offensive doctrine. That's strategic dominance at the highest level. The wear and tear on the 88's barrel was precisely calculated. After 1/500 rounds, the muzzle velocity decreased by approximately 50 meters per second. After 3,000 rounds, by 150 meters per second, the penetration power reduced proportionally. German crews maintained meticulous shot counters. At 2,800 rounds, the barrel was routinely changed. Not at 3,000, but 200 rounds before. This precaution guaranteed maximum performance. Soviet cannons were used until absolute failure. German engineering philosophy was different. Replace the part before it fails, not after. The 88 could also be used as an indirect fire weapon. With special angle finders and fire control computers, it could engage targets up to 15 kilometers away, without direct line of sight. This capability was rarely used, but it existed. Allied reconnaissance discovered 88 batteries in Italy in 1944, conducting artillery fire. The precision was astonishing. British artillery observers reported German 88mm shells landing within a spread of only 30 meters at 8 kilometers distance. Normal artillery had a 100-150 meter spread. Even as a makeshift solution, the 88 surpassed specialized artillery systems. The ammunition logistics were a German masterpiece. Each 88 battery had standardized ammunition wagons. Each wagon carried 24 shells in climate-controlled containers. The temperature of the ammunition influenced the ballistics. German textbooks specified optimal ammunition temperature, 15 degrees Celsius, plus or minus 3 degrees. In colder temperatures, the ammunition was warmed before use. In hotter temperatures, cooled. This attention to detail was typically German. Soviet ammunition was simply transported and used, regardless of temperature. The 88 also saw action on the Eastern Front against Soviet tanks. The T-34 with its 45mm armor and the KV-1 with 75mm were considered invincible until they met the 88 on June 23, 1941, just 2 days after the start of Operation Barbarossa. A single 88 battery near Raseiniai in Lithuania destroyed 43 Soviet tanks in 6 hours. The Soviet commanders were shocked. Their newest tanks, which were supposed to repel all German tank cannons, were being penetrated at 2,500 meters distance. The Soviet Major General Dmitry Paulo wrote in his report, "We have technically nothing that equals this German weapon." The acoustic signature of the 88 was unique. The muzzle blast generated a specific double bang, first the pressure wave, then the sonic boom of the supersonic projectile. Experienced Allied soldiers could identify an 88 by its sound. Veterans of Normandy described it as a sharp, whipping crack, followed by a deep boom. Unlike any other weapon, this signature became the acoustic symbol of German military superiority. After the war, the People's Republic of China attempted to obtain 88 technology from the Soviet Union. The USSR supplied blueprints of the Soviet copies, not the German originals. Chinese engineers developed the Type 56 85mm cannon. It was based on Soviet designs, which in turn were based on German technology, a copy of a copy. The performance was correspondingly reduced. The Type 56 achieved 780 meters per second muzzle velocity, to 20 meters per second, slower than the German original from 1933, 3 decades later, and 3 technology transfers removed. The Chinese version was significantly weaker. The 88 also proved amazing reliability under extreme conditions. In the North African desert at 50 degrees Celsius, in the Russian winter at -40 degrees, in the mud of Italy, in the dust of France. The hydraulic systems continued to function. The mechanical parts rarely failed. German designers had integrated solutions for every environmental condition: special seals for heat, antifreeze for cold, dust filters for deserts. This robustness was no accident. It was the result of systematic testing programs in all climates before mass production. The ballistic computers for the 88 were mechanical marvels. The Commando Giret 40 weighed 130 kilograms and contained over 2,000 mechanical parts. It continuously calculated lead angles for moving aircraft. Inputs were target speed, target direction, distance, wind speed, own movement, output, precise elevation and azimuth. All mechanical, without electronics. The accuracy was astonishing. The device could calculate lead angles with 0.05 degrees precision. American equivalents only came onto the market in 1943 and were less precise. The 88 as an anti-aircraft weapon was equally legendary. In the defense of the Reich territory from 1943-1945, 88 batteries shot down an estimated 17,000 Allied bombers. The weapon could effectively fire at altitudes up to 14,700 meters. B-17 bombers typically flew at 7,500 meters. The 88 reached them effortlessly. Allied bomber crews developed specific tactics: fly higher to get out of the 88's range, or fly very low to stay below the detection range. German anti-aircraft defenses forced the Allies to adapt their entire strategic bomber doctrine. The production cost of the 88 was approximately 33,600 German mark per gun in 1942, roughly 280,000 euros in today's purchasing power. A Tiger tank with its 88mm WK-36 cannon cost 250,000 German mark. The standalone 88 was a fraction of this cost and achieved comparable tank destruction. The cost effectiveness was mathematically overwhelming. A Tiger could destroy 5 enemy tanks before it was destroyed itself. Statistical average. A well-positioned 88 could destroy 20-30 tanks and often survive the battle. The cost-benefit ratio was 10-to-1 better. The tactical flexibility of the 88 was unique. It could switch from march position to firing position in 2.5 minutes. It could engage aircraft, tanks, bunkers, infantry. It could fire directly or indirectly. It could operate stationary or mobile. No Allied weapon had this versatility. Soviet attempts to develop an equivalent multi-purpose weapon failed. The D-44 was too heavy for rapid mobility. The ZAS-3 had too little penetration power against heavy tanks. The 88 remained the only truly universal gun of World War II. The post-war use of captured 88 guns is well documented. Yugoslavia employed captured German 88s for coastal defense until 1962. Finland retained its guns, captured during the Continuation War, in active service until 1977, a full 32 years after the war ended. The Soviet Union used functional 88 guns along the Chinese border until the late 1940s. Egypt received Soviet copies of the 88 in the 1950s and deployed them in the 1956 Suez Crisis. The technological legacy of the 88 spanned decades and continents. Today, 88 guns stand in museums around the world. The Imperial War Museum in London has 3. The German Tank Museum in Munster has 5 in various configurations. The Kubinka Tank Museum in Russia has 2 trophies from the Eastern Front. Each preserved example demonstrates the same quality: precision manufacturing, thoughtful design, robust construction. Even 80 years later, the mechanical tolerances are apparent. Modern engineers examine these museum pieces and still find innovative solutions that could be applied today. The lessons learned from the 88's development continue to shape military weapons systems. Modularity, parts should be interchangeable. Versatility, a weapon for multiple purposes is more efficient. Precision, technical superiority beats numerical superiority. Training, well-trained crews magnify effectiveness. Quality, robust construction pays off in the long run. These principles, embodied in the 88, are now NATO standards for weapons systems development. If you want to learn more about German engineering in World War II, subscribe to this channel. We reveal technical details that changed history. Click the bell for notifications. Share this video with anyone interested in military technology. The history is complex. The technology is fascinating. The lessons are timeless. The question remains, why couldn't any other nation develop an equivalent weapon during the war? The answer lies not in a single factor. It was the combination of metallurgy at the highest level, hydraulic precision, optical excellence, ballistic science, systematic testing methodology, quality control down to the smallest detail, comprehensive training. These elements together created a weapon that was 10 years ahead of its time. The Allies caught up, but only after the war. The Soviets copied desperately, but never matched the original. The 88 remained a symbol of German engineering at its finest. What technical details of the 88 impressed you the most? The 1,000 meters per second velocity, the 0.1 degree precision of the aiming system, the fact that Soviet copies took 17 years to achieve equivalent performance. Write your thoughts in the comments. Discuss with other technology enthusiasts. The story of the 88 is the story of engineering against all odds. The evolution of the 88 itself shows German perfectionism. The Flak 18 of 1933 was already superior. The Flak 36 of 1936 improved mobility. The Flak 37 of 1939 added improved fire control. The Flak 41 of 1941 increased the muzzle velocity to 1,130 meters per second. Each iteration was an improvement. Each version integrated lessons from combat. Continuous improvement was not a phrase, but doctrine. Allied weapons often remained unchanged for years. German weapons constantly evolved. The 88's gun carriage design was also innovative. The cruciform mount allowed 360-degree rotation without repositioning. The 4 stabilizers could be deployed in 30 seconds. Each stabilizer had adjustable height for uneven terrain. The entire system was modular. Damaged parts could be swapped in the field. Soviet designs often had permanently welded components. Repairs required transport back to the factory. German modularity meant on-site repair in hours, not weeks. Ammunition production for the 88 reached astonishing volumes. In 1944, Germany produced 3.1 million 88mm shells, despite constant Allied bombing. Quality control remained strict. Each shell was weighed. Deviation was allowed only plus or minus 20 grams on a 9.5 kilogram total weight. That's 0.2% tolerance. Modern ammunition production achieves 0.5%. German war production under bombing was more precise than modern peacetime production. That is statistically remarkable. The 88 crew consisted of 11 men in full configuration: commander, gunner, loader, fuse setter, 4 ammunition handlers, 2 drivers for the towing vehicle, a mechanic. Each had specific tasks. Each was trained for 2 or 3 additional positions. This redundancy was life-saving. Combat reports show 88 batteries with 60% personnel losses continued to remain operational. Soviet artillery with similar losses had to cease operations. The 88 also fundamentally influenced post-war tank design. The British Centurion received a 20-pounder gun, developed in response to the 88 threat. The American M103 heavy tank with 120mm gun, a direct evolution from the need to engage 88 positions at range. The Soviet T-54, with its strong turret front, designed to withstand 88mm hits. A German weapon dictated 3 decades of international tank design. The electronic fire control of later 88 variants was ahead of its time. The Würzburg radar could acquire targets at 70 kilometers and transmit fire control data directly to the 88 batteries. The system achieved full operational readiness in 1943. American equivalent systems didn't arrive until 1944. Soviet systems only in 1948, after the war. The integration of radar and artillery was a German innovation that is now standard in all modern air defense systems. The survival rate of 88 crews was higher than that of tank crews. Statistical analysis shows a Tiger tank crew had a 73% chance of suffering losses after 6 months of deployment. An 88 crew, 41%. The reason was mobility and range. The 88 could fight from a distance and quickly retreat. Tanks had to get closer and were more exposed. The weapon protected its crew better than its armored counterparts. The 88 also had an unexpected side effect on Allied tactics. American tank commanders developed the Thunder Run tactic, a rapid advance at maximum speed to break out of the 88's firing range. British units developed the creeping barrage tactic, massive artillery fire ahead of the tank assault to suppress 88 positions. Soviet doctrine shifted to mass tank assaults, overwhelming the 88 through sheer numbers. Every Allied nation had to adapt their tank warfare. One weapon forced 3 superpowers into tactical evolution. The Flak 88 maintenance manuals spanned 2,347 pages. Every part had its own maintenance intervals. Every system had diagnostic checklists. The hydraulics needed checking every 50 operational hours. The sight needed adjusting every 100 operational hours. The barrel needed cleaning after every 500 shots. This systematic maintenance extended its lifespan and guaranteed reliability. Soviet weapons often had one-page maintenance instructions. German thoroughness in documentation was as important as thoroughness in construction. The 88 also played a role in the development of modern projectile tracking. In 1944, German engineers experimented with tracer rounds for the 88 that remained visible even during the day. The goal was to enable real-time correction of fire. The technology wasn't mature before the war's end, but the concept influenced post-war developments. Modern anti-tank systems, like the American Tau missile, use this principle, developed from German 88 experiments. The international proliferation of 88 technology after the war is extensively documented. Sweden developed the Bofors 75mm under license from Krupp engineers. Spain produced a local version until 1965. Argentina imported German engineers who developed a modified version. South Africa used captured 88 guns into the 1980s. The global technological diaspora of the 88 is unprecedented for a single weapon. A cost-benefit analysis of the 88 from a modern perspective is illuminating. One gun cost approximately $300,000 in today's purchasing power. Average lifespan, 4.7 years in active service. Average number of targets destroyed, 37 tanks or 8 aircraft. A modern Javelin anti-tank system costs $200,000 per missile. One missile destroys one target. The 88 was 37 times more cost-effective than modern single-use weapon systems. This calculation explains why reusable precision weapons are now a military priority. The 88 also demonstrated the limits of numerical superiority. On the Eastern Front, German troops were often outnumbered 3-1 or 5-1, but 88 batteries offset this numerical disadvantage. A single battery with 4 guns could halt a Soviet tank brigade with 60 vehicles. Technological superiority, precise fire from a great distance, defeated raw numbers. This lesson shapes modern military doctrine. Quality can overcome quantity when the technological edge is great enough. The last documented combat use of an original German 88 was in 1995 in Yugoslavia during the Balkan conflicts. Serbian forces used a 50-year-old gun against Croatian T-55 tanks. The gun functioned. It hit its mark. It destroyed 2 tanks at 2,000 yards. After half a century in storage, the 88 proved its robustness one last time. This anecdote shows German engineering from the 1930s was still dangerous in the 1990s. The 88 represents a pinnacle of mechanical engineering. No microchips, no digital controls, no computer calculations. Just steel, hydraulics, precision manufacturing, and mathematical excellence. It proved, with perfect mechanics and brilliant design, simpler systems can beat more complex ones. This philosophy, perfection through simplicity, is perhaps more relevant today than ever. In a world full of overcomplicated systems, the 88 wasn't just a weapon. It was a demonstration that thoughtful engineering creates timeless superiority.